Hello, I'm going to present the paper Learn Codes Inventing Low Latency Codes via Recurrent Neural Networks. My name is Varun and my other teammate name is Lakshman. Uh, Coming to the contents, I'm going to introduce the paper and what is the main aim of the paper. And next, I will explain you one of the how the rec- uh, channel encoder with recurrent layers in it will outperform some of the conventional channel coding schemes. And next, my friend will explain about the learn code and its performance. Uh, so, channel codes have a huge impact in the communication in this modern information age. There are several channel capacity. There are several channel codes like polar codes, turbo codes, and LDPC codes, which has come close to the Shannon capacity uh, when they are operated at the large block lengths. Now our main aim is that we need to have a code such that it has low latency and it is robust and it will adapt to the new channel settings. So an ultra reliable low latency channel communication code generally requires minimum delay constraints. So if it has a minimum delay constraints, it can be applied to the real life scenarios, um, like in the vehicular communication and virtual reality and some for remote surgeries, etc. Now, if we are going to have a minimum delay, if we are going to have a minimum delay constraints, we need to have less propagation delay. When we come, we need to have less delay. When we come to discuss about the delays, there are three types of delays like the processing delay, propagation delay, and structural delay. The processing delay and propagation delay generally arises due to the computing resources and the environment conditions. The structural delay is something where we can where we can do some coding and improve that part. So for a structural delay means like for a system means what is the time it will take for to give the output for a given input at time instant. If we give the input at a time instant t, so at what time instant this output, how this model is giving the output, so that delay is generally stated as the structural delay. So for the block for the block codes, the latency generally scales with the block lengths. Like the decoder has to wait until it has all the bits in the current block. If the block length is very large, the decoder has to wait so much time uh, than the one which with less block length. For the convolution code, this latency generally depends upon the this convolution window size. So if it has a large window size, generally it takes the has high latency, and if it is a less window size, it has a low latency. So the main focus is to have the low latency conditions, and it has to be robust and adaptive. So robustness means like refers to like the ability to perform with the acceptable degradation without retraining when the model mismatch occurs. Like when we train a model in one of the channel setting, and if we test that model in a different channel setting, the model performance shouldn't like degrade too much. If it is degrading too much, it is not robust. If it withstand that new setting also, we can say that that model is robust in that new setting. And regarding adaptivity refers to the ability to learn to adapt to the different channel models with retraining. Like if we train the model in one of the setting, and if we want to uh, like if we train with some of the samples of the new channel settings, and if it is if it is performing well by that by that retraining with the only less samples also, then we can say that it is adapting to the new channels also. So this is what the adaptivity means in the current scenario, what I'm saying. Next I'm going to explain uh, where the channel coding where the sorry I mean where the deep learning is used in this channel coding here. Like, in developing the codes for an L2 wide Gaussian noise channel under low latency condition, um, we we have a challenge of optimal codes and the decoding algorithms. So it means we don't have some best optimal codes and decoding algorithms. So it has some algorithm deficiency there. So in those cases, we are going to use the deep learning networks there. So there are two types where we can use the neural network at the decoder, and at the encoder part we will use the uh, LDPC codes or the turbo codes. And the other thing is like where we will use the neural network at both encoder and decoder, and they are trained sequentially, and that is called an autoencoder. These autoencoders has shown successful application in dimensionality reduction and the representation learning and graph generation. So we need to have a channel autoencoder in such a way that it has to generalize to unseen messages, and it has to be highly robust, because the information sent from an encoder is going through the channel where the noise is going to add to it. So the decoder must be like robust to the noise added by this channel also. So we need to have the autoencoder totally robust to this noise added by this channel, and it also has to satisfy the power constraint. uh, we have some papers on the where this in the autoencoder part, where they will use the fully conventional only, they will use the fully connected neural network there. If I pronounce somewhere in between like conventional, it means like convolutional, like it means like connected, like FCN, fully connected neural network, right? Sometimes I will use conventional because you can get it right. So where am I? Yeah, there are some papers where previously where the in the autoencoder part where they used only fully connected neural networks only, but now in this paper we are going to see how if we use recurrent neural network in place of FCN in the autoencoder, how it is going to perform, whether it outperforms or it degrades the performance. We'll see how does both. But to our surprise, this RNN based channel autoencoder outperforms the convolutional code. Here we are going to use the bidirectional recurrent neural network there, here at both the encoder and the decoder part. And why we are using recurrent neural network is, um, recurrent neural network has some natural connection with the convolutional codes, because they depend upon the local memory and some of the past bits. So recurrent neural network is also something where the output at the current stage depends upon the past inputs also. So it has some connection there. Now I'm going to explain how the neural codes is outperforming these convolutional codes here. Traditional channel codes performance improves generally with the block lengths, and if we see two of the graphs here, where in the if the blue lines here, the blue line in the graph says if we in the autoencoder we used only fully conventional neural network, and in the green graph shows where we used the uh, green in the green graph shows where in the autoencoder we used the recurrent neural network. Recurrent neural network. So we can see that the channel autoencoder with a recurrent neural network in it is outperforming the one with the FCCN here. In the low, but in the block, if the block length is very less, we can see that FCCN and RNN are pretty close to each other. But if we go for larger block lengths, the RNN based channel autoencoder outperforms the FCCN based channel autoencoder. And we can even see that this RNN based channel autoencoder even outperforming the conventional channel coding schemes, like the repetition code has the has the high bit error rate than the ones. And here the RNN is outperforming this fully conventional neural network because of its parameter sharing and adaptive learnable dependency length. We are going to achieve this power constraint by introducing a new block here, power constraint block after the encoder, where we will normalize the power here after the encoding. Now I am going to tell about the network. So you can see that in the encoder part we have two bidirectional graded recurrent units and an FCCN, and in the decoder part also we are going to have the bidirectional graded recurrent units and a FCCN. And we can see that decoder has the more capacity. I mean, it has more parameters than the encoder, because we want to make sure that decoder is more generalized. I will tell you why we want to have the decoder more generalized in the coming slides. And this channel autoencoder is trained for the large batch size, and we have used the binary cross entropy loss here, and we use the minimum distance regulator on the encoder, and the Adam optimizer is used. Next, I'm going to explain how the performance will be in the L2 wide Gaussian noise setting. How this recurrent uh, recurrent neural network, how this channel auto encoder with recurrent units like GRU units in it will outperform the conventional code here. So if you see TBCC, which is the tile bit convolutional code, which will show great results for the shorter block lengths. So it is we are going to compare with the TBCC and the channel autoencoder here, RNN based channel autoencoder here. So at a different rates, we can see that this RNN based channel autoencoder is outperforming this TBCC in the L2 wide Gaussian noise setting. Like the model is trained in the L2 wide Gaussian noise setting only, and the TBCC is also performed in the L2 wide Gaussian noise setting only. And next, we are going to compare the results in an L2 wide Gaussian non-L2 wide Gaussian noise setting, and also we are going to test how this RNN based channel autoencoder is robust and adaptive to the new settings in this through these graphs. Like there are two other channels we are going to use. They are the additive T distribution noise channel and the radar channel. So if you can see here, this this green line, this blue line represents the RNN based channel autoencoder in all these three. And here this yellow line is the one where the decoder part we used some of the training samples from the different channel settings for training the decoder part. decoder part only, and this green line with points with this cross points shows where the encoder part and decoder part is used, where the encoder part and decoder part is trained with some of the samples from both the encoder and decoder are trained with some of the samples from the other channel setting also. Only some samples are used, and this purple line shows that conventional, the tail bit convolutional code. So we can see that in all the three graphs at with the rates are different, like 1 by 2, 1 by 3, 1 by 4. We can see that the the blue line, which is the RNN based channel autoencoder, has low bit error rate than the TBCC graph, which is the purple line here, which means it is robust at a different, which means it is robust means the channel which is the model which is trained at one channel setting is even performing well at the different settings also. And if the blue line says where the decoder part is trained, this yellow line shows where the decoder part is only trained for some of the samples from the different channels, like from the radar and the T noise, I mean additive T distribution noise channel. We can see that this yellow line is even less than the like bit error rate is even less than the normal one where it is not trained from the other samples, like the blue line. So it is getting adapted to the different channels also by only training the decoder also. But if we train both uh, encoder and decoder part of the autoencoder, it is getting even less bit error rate here. And these all these all channel autoencoders are outperforming the convolutional codes. So we can say this RNN based channel autoencoder is robust, and it is getting adapted to the new channel setting, is even getting adapted to the new channel settings also. Now next my friend is going to explain you about the learn codes. Thank you.
So, designing low latency uh, codes is very challenging, since many of the existing codes which are already present have very long block lengths, which means there is a lot of delay while decoding and encoding. So here we'll look at an RNN based encoder and decoder architecture, which will which it tries to reduce the latency of the channel. So learn codes means low latency, efficient, adaptive, robust neural codes. By the end of these slides, we'll show that learn code basically is significantly more reliable than the state of the art convolution codes which are used for low latency applications. And learn codes are more robust and also adaptive for various channels, uh, not only beyond AWGN channel. So we'll be making convolution codes as a benchmark, and we'll be comparing these with our learn codes. We'll use the best possible convolution codes with variable memory length. So a little about convolution code. Convolution code has zero encoder delay, but at the decoder, it it has a delay d, after which it decodes bit bt. So it has a decoder structural delay of d. Here the convolution code which was used was a normal causal encoder and a Viterbi decoder. The best possible latency which we have as of now with convolution code is 50, but with the learn codes we can bring it down to 1 to 10 for the same bit error rate. So a little now we'll discuss about the learn network architecture. As discussed before, the architecture which was told by Varun, the same thing is used here. Instead, there is a change in the decoder part. For the encoder part, the architecture remains same by RNN, with two layers, and then followed by a fully connected neural network. But for the decoder part, instead of using a bi-RNN, we use a single RNN, which is GRU, gated recurrent unit, it's also called. So we do this because in applying the bi-RNN, there is a look ahead. We calculate the look ahead instance for each information bit, which is computationally expensive in both memory and time. So instead, we use a single RNN, but use it of two layers, but use it two times parallelly, and then finally followed by a fully connected neural network, and then which gives the message BT. So here we showed the dimensions of both the encoder layer and the decoder layer. So coming to the results, so here we have bit error rate versus signal to noise ratio for the same delay of 1 or 10. Here for the same delay we can see that the learn codes show a very less bit error rate when compared to the convolution code. From this we can conclude that the our learn codes are much efficient than the convolution codes. So here, but yeah, here we have two different graphs, one for the delay of 10 and one for the delay of 1, from increasing rate from 1 by 4 to 1 by 2. So in conclusion we can say that our learned codes will significantly outperform the convolution codes in short to medium block lengths. And one more thing is that these are very adaptable and robust, in the sense convolution codes will only work mostly for the AWGN channels, but the learn codes are not only for the AWGN channel, they also work for many other channels. They are very adaptive in that sense. Thank you.